Hello and welcome to the first session of our Sports Aerodynamics Workshop by SimScale in collaboration with EM Sports Science. Yes, it's great to see so many people who have joined for our first workshop about sport aerodynamics. And today or during the next 3 weeks we will learn a lot about the impact of aerodynamics on the performance of top athletes. Before we actually start to dive in our today's topic, I would like to make sure that everybody can hear me loud and clearly. Therefore, in the case you can hear me loud and clearly, please click the raise your hand button so that I know everything is working fine. Yes, today is our first session where we will talk about the aerodynamics of a ski jumper. And let's first of all talk a little bit about today's agenda. So first of all, I will just give you some very crisp information about this workshop series. So what is the aim of the workshop series, what we are going to do the next couple of weeks. Just after that, we will talk again about the very fundamentals of aerodynamics, which you should know to be able to understand the topics we're going to talk about during the session. And after that, we will have a live demo where we will show you, first of all, how aerodynamics is influencing the total performance of a ski jumper, and also how to leverage the SimScale platform to create your own CFD simulations of a ski jumper. Yes, let's start. What is the idea of this workshop? So a lot of people ask us that they are very interested in the application of aerodynamics in medicine and sports, and if it would be possible to host a workshop about sport aerodynamics, and that's the reason why we have organized this workshop series. So the idea is to share interesting insights with you about the impact of aerodynamics in sports. And also, in the case you never heard about simulation or never worked yourself with simulation, to give you some first-hand experience about simulation. Therefore, we cannot talk about everything. So this workshop is not training on simulation theory. If you're interested like in the fundamentals of simulation theory, especially about the mathematical background and physical background, we have a lot of other free training resources on simscale.com which you can access. And also in the case if you're interested in the practical application of simulation in design projects for developing products and commercial use, we also have some other resources you should check out. And again, because a lot of people are asking why we are hosting these workshops, we really believe at SimScale that simulation is a technology that should be used by every engineer around the world, because it allows you to develop your product much faster. And therefore, our main idea is that we want to introduce interested students and engineers and designers to sports simulation or engineering simulation. And for sure, we also like to receive product feedback and contribution to our simulation library. And in the case you've joined in the past one of our workshops, I think you basically know what the concept is, but let's just talk about very crisp. So we will have 3 one-hour online sessions with a live demo, and every session is focusing on the different aspect of sport aerodynamics. During these sessions, you will learn some fundamentals about the physics, and as well as how to model this kinds of physics using engineering simulation. And after every session, you will have an optional homework assignment, and submitting all 3 homework assignments will qualify you for a certificate of participation. And we will later talk about the homework, but you can share them using a form on simscale.com. We received a lot of questions, and since some of them were asked very frequently, let's just talk about them. So first of all, yes, we will record every workshop session. So in the case you cannot join for a workshop session because you have another appointment, you can just watch the recording. We will send the link with the recording to all registrants just after the session. In the case you want to work on the homework assignment, please wait until the session is finished. You have more than 1 week for work on your homework, and you should use this live session mainly for ask questions. And in the case you have questions, we have a question window. It's in this GoToWebinar control panel. And there you can very easily ask a question, and my colleagues will answer them directly, or we'll talk about them later during the Q&A. And in the case you have troubles with setting up your own simulation, we have prepared a dedicated forum section on simscale.com where you can find help. Okay, great. So now let's start to dive into our today's topic. And first of all, let's just talk again about some very important fundamentals of aerodynamics. I know that a lot of you already have some basic knowledge, so let's try to keep it very short. And for sure, if we start to talk about aerodynamics, there are a lot of very important aspects. But since we want to apply this knowledge, let's really start with the most important basics. So first of all, I think you all know what aerodynamics is. Aerodynamics is in the end a science which is dealing with the motion of fluid flow around objects. And a fluid basically is everything which is not solid. So gases as well as fluids, gases as well as fluids are called fluids. And when we talk about the interaction of such a such a flow with the body, there are basically two zones we have to consider, and this is very important and to understand also what is happening inside the flow field. Let's imagine, let's take this airfoil section, and just imagine how the flow around this airfoil section will look like. And for example, I will just take my pen. If we have flow from here and would streamline, so the flow would stream around this body. And there are a lot of things happening inside this flow, and here we have to differentiate between two zones. First of all, we have an outer flow, which is very far away, let's say far away from the body. And there we can nearly neglect all viscous effects. And we also have a zone 2, which we call the boundary layer, in which the viscosity effects are predominant. And the reason is that we have a friction, we have viscous effects inside the flow, and here at the surface of the wing, the velocity is 0. So here we have a stick condition, which means that here the velocity is exactly 0. And if we go far away from the wall, somewhere we will have, let's say, the outer flow velocity. And in this area we get a velocity profile. So the velocity is changing massively from 0 on the surface till we to the outer flow value we have in the zone 1, in this inviscid fluid zone. And inside this boundary layer, a lot of physical things are happening. So we have a lot of energy exchange, and basically everything which is later happening inside the flow field is somehow impacted by the boundary layer. And sorry, you see that? Now let's go further. Yes, and if we take a look at this boundary layer, at this zone 2, we can see this here. You can see a sketch of this velocity profile. So let's imagine we have this flat plate, we have flow coming from the left side with the velocity u infinite, and then we have here the boundary layer, and you can clearly see that we get this velocity profile which I talked about. So the velocity on the plate itself is 0, and it increases to u infinite. And in the end, our boundary layer is defined by the velocity itself. So everywhere where the velocity is lower then 99% of U infinite, we have the boundary layer. And this is very important to understand because we will later talk about effects like flow separation, where flow is not following any more surface, and this is very much related to the boundary layer. And this is a very good example. Here we have a curved plate. Just imagine we have the flow coming from the left side. And one thing which is very important is to understand the relation between, let's say, pressure and velocity. So inside the flow field, the pressure in the end, which you know we can divide into total pressure, dynamic pressure, and static pressure, is in the end the energy in the flow. And if this flow is like following a surface, it's running again a pressure gradient. It means the pressure is changing in this direction. And as long as this velocity profile, let's say it's positive, so all vectors are showing in the direction of the infinite flow, the flow will attach on the surface and follow the surface closely. But at some point, as I mentioned, the pressure is changing also during this path. At some point, it cannot follow anymore the surface, and the reason is the following. With the airstream, or inside this airstream, we have energy, kinetic energy somehow. And this kinetic energy is used, or it's converted, let's say converted, it's maybe a better word, it's converted into pressure energy. And when the energy of the boundary layer is not enough to run against this pressure gradient, we will have a flow separation, what we call, as you can see here. And this point D, where the flow starts to separate, is called separation point. And yes, now we recap the basics of aerodynamics, and now let's start to apply this on ski jumping. So first of all, I've prepared some images for you which show a ski jumper, and this is a very nice image because it was taken from the same perspective several times, and so we can really follow the path of the ski jumper. And let me just take my pointer. And so you can see the ski jumper is driving down this ramp. Here, when the ramp is ending, he's like jumping, and then he is flying. And in the end, ski jumping is about to go as far away as possible. And physically, what is happening? Here, we have a very high potential energy because the height distance. So let me just take my marker again. Sorry, my pen. And here, this difference, h, the height. And as you know, the potential energy is depending on the height, distance, and the gravity. And so when he is driving down this ramp, he is converting his potential energy into kinetic energy, which means the ski jumper gets accelerated. And he will reach his maximum velocity, in theory, exactly here, at the lowest point of the ramp. And as you can see on the image here, they are then like taking off and try to fly. And this is very important to understand what is happening here, because if we take a look here, for example, we have several forces acting on the ski jumper. We have here m mass multiplied with g. G is the g-force, so the gravity, which is like pressing him down. Since he is flying through wind, we also have Fd, it's a drag. And this is very important. The ski jumper itself is generating somehow a force we call lift. It's, by the way, the same force which makes the airplane fly. And in the end, these three forces are in the end describing the path, the trajectory of the ski jumper. And as you can imagine, the gravity is not changing, as well as the mass of the ski jumper is not changing. So in the end, this whole trajectory is described by the lift and the drag forces. And so these forces are very important, and they depend on a lot of different things, mainly on the posture of the ski jumper. And that's the reason, and you can see very clearly why he is changing his posture during the flight, because at the full phase of the flights, he wants to have difficult aerodynamic conditions. And if you take a look at the history of ski jumping, the way they are jumping changed a lot during the years. So till, for example, the mid of the 80s, you can see here that they are have a V shape with the skiers. They didn't use this V shape, they just had the skiers in parallel. And also how they changed the angle, for example, between the chest or the whole body and the ski jumper here. These are all parameters which can highly affect the aerodynamics of the ski jumper and therefore the aerodynamic forces, and in the end this also impacts his flight trajectory and the maximum distance he can fly. Guys, just because some of you asked me, unfortunately I don't know why I cannot hide this control panel. I already know that it's there, but I just have to put it down. Sorry for that. It's a technical issue with GoToWebinar. Okay, then let's go on. And as we promised, we will talk today about aerodynamics of a ski jumper, and therefore we have prepared two parametric studies of a ski jumper, and we varied the angle of the track between the skis and the ground, as well as the V angle between the skiers. And we will just in some minutes show you the results of this parametric studies and discuss them together. And then you get a first impression of the impact of aerodynamics on the performance of the ski jumper. So first of all, I would like to talk with you about simulation, because we used simulation to create this parametric studies, and I think this is a very good example what is the advantage of simulation, because if you take a look at the conventional design process timeline, you have to design your model, build the prototype, test it, and then you can take design changes and try to improve it. If we apply this process on a ski jumper, that would mean we have to build a physical model of the ski jumper. So we would have to rent a wind tunnel facility, test it, and in the case we find out some parameter we wanted, which seems to have a big impact, was not investigated by us, we have to start again from scratch. In contrast to that, simulation allows you to create virtual experiment based on CAD data, based on digital blueprints of your design. And this is not only limited to physical technical products like a valve, but you can also take a CAD model of a ski jumper, for example, and then virtually test. And this allows you to get better results much faster and much cheaper. And SimScale is hosting the first web-based or cloud-based simulation platform. So simulation basically it's a struggle to, or it was in the past, it was a big struggle to use simulation, because you had to make sure that you have the right hardware, the right software licenses, etc. And SimScale is a web-based tool. So everything you need to create simulations with SimScale is a web browser and an internet connection. And within our web-based platform, you can create a lot of different simulation types for, let's say, nearly all kinds of physics, starting from flow simulations where we have aerodynamics, like aerodynamics of a ski jumper, or internal flows and other stuff, or also structural simulations and stuff like that. And the great thing about SimScale is that it's, first of all, it's a free end-to-end CAE workflow, so every one of you can use it for free during and after this workshop to create his own simulation. And it brings together also content and people. You will see it later. SimScale has a large library of public simulations you can access and use for free. And also SimScale is the largest community of simulation engineers. So whenever you need help, you can discuss your questions in our forum. And we have a lot of resources at SimScale. You know already one of them. It's our webinars and workshops, but we also have, as I mentioned, public projects. We have a forum, free tutorials. So wherever you need help, you will find it on SimScale. And now let's just quickly talk about what a CFD simulation or a fluid flow simulation is. Because it sounds like magic, but basically it's very easy. So CFD stands for computational fluid dynamics, and it's a kind of virtual wind tunnel. And in this virtual wind tunnel, we'll put our ski jumper under varying conditions. And to understand basically what a CFD simulation is doing, you have to know that a flow can be completely described by velocity and pressure. So in the case, let's take example this wings here. In the case, for all points around your wing, for all points in the flow field, velocity and pressure of the fluid, you can exactly describe the flow. And what we in the end try to do with a CFD simulation is to get this information. And there is a good news. Let's say some good news. The good news is there are some physicians and scientists more than 200 years ago already found out the equation, which is like linking velocity, pressure within the flow field in space and time. But the problem is that we cannot solve them directly, but I will talk about this aspect later. In the end, the idea of CFD, of a fluid flow simulation, is that within our flow field, we have a conservation of mass and momentum, which means everything which gets in also has to get out. So if we take a look, for example, at infinite small volume of our flow field here, all the mass with the flow which goes in goes out, or to put it another way, if we have a change of rate inside this element, it's a difference of the incoming and outgoing mass flux. And the same for momentum. So the change of rate of momentum is the difference between incoming and outgoing momentum of the flow. And since we cannot solve this equation analytically, we will do it numerically. Which means instead of solving all infinite number of points inside our domain, we will just pick certain number of points and only calculate a numerical solution of these equations inside those points. And this allows us to solve this equation. And at the final step, we will get for every of these cells, we call them cell, a value for velocity and pressure. This for sure means that a fluid flow simulation has a limited accuracy. There is not a 100% accurate flow simulation, but by increasing the resolution of this element at the right areas, in the areas where we have a lot of change, we can get a solution which is very good and good enough for analysis and use in engineering and design. So if we take a look at the process of a CFD simulation, there are 3 steps. The first step is called pre-processing, which means you have a digital model of your ski jumper, in this case a CAD model. But this CAD model is maybe not necessarily perfect for a fluid flow simulation. Just let me give you a very simple example. If you have a small gap inside this model, it would destroy your whole simulation because then air would go inside the ski jumper. And pre-processing is the first step of a simulation, which is about preparing the geometry. And after the geometry was cleaned up and prepared, it's about meshing the geometry, which means dividing the geometry into small elements which we can solve. Next step is to define the simulation itself. So we define where the air goes in, where it goes out, and for example, which kinds of walls we are dealing with. And the final step, called the post-processing, is the evaluation and analysis of the results. Yes, as I said to the beginning, we have prepared such a study, and I will just quickly to show you how this looked like, just that you know what we are talking about. So this is simulation project my colleague Krishna prepared for this workshop. And here you can see the three-dimensional model of the ski jumper first of all. And we have changed different things. For example, we have for every parameter we have our own model. So this is a baseline model. This is and to compare it, this is a model with a V angle of 0. So we have parallel skis, which you can see here. And as I described, the first step is about creating this mesh around the ski jumper. And since we are interested in the flow around the ski jumper, we have to create the mesh also around the ski jumper model. And if we take a look, so you can see that we've defined a domain, which we will investigate later on. And inside this domain, we have our ski jumper. And as you can see, the mesh at the surface of the ski jumper is much finer than the mesh outside, which makes sense because we're interested in the flow in the near around the ski jumper, not far away. And to create this mesh, basically what you do, you are defining a bounding box around your object. You're defining a material point, which is telling you where your object is located. So in this case, we put the material point somewhere outside the ski jumper. If we would put it inside the ski jumper, the mesh would be inverted and it would be a mesh of the ski jumper. And we also created a refinement zone, which we will show you later. And then in the end, you just define different refinement, so different element lengths for different surfaces and different regions. And then you just click on run operation and you get this mesh. Just after that, we used the mesh to set up a simulation. So in the end, what we did is we defined the material, it's air, and we defined the inlet, which is this surface here. Sorry, so this is the inlet. This is the outlet. And we use different boundary conditions, which means that we have to tell the fluid flow solver, the CFD tool, what you should calculate. So therefore, for example, the ski jumper is defined as a non-slip wall. And then the final step is analyzing the results, which you can also do within the SimScale platform in 3D using a web browser. And just to give you a very quick example, I will show you something I've prepared. It's a pressure distribution around one of the ski jumper models. Just takes some seconds to load since it's a quite large data set. And now you can see the ski jumper and the pressure distribution around the ski jumper. Okay, but today we want to discuss mainly the results, and therefore I'm very happy my colleague Akram also joined, and we will together now guide you through this parametric study and discuss the results. Akram, can you hear me?
Hey, I can hear you. Can you hear me?
Yes, we can hear you too. Great.
Hey everybody, and good evening from here, and good morning, good afternoon, good evening, wherever you are around the world. I'm so glad to join you for this presentation where we will give you the basics about the aerodynamic of ski jumpers with this parametric study of two parameters, the angle of attack and also the position of the feet, what we call the V angle. And me and my colleague and I we will try to give you the basics about this application. So yeah, Milad, go ahead and let's discuss the next slides.
Yes, sounds good. So we will start with the first parameter, the angle of attack. And here we can see basically three plots. One is showing lift, the other one is drag, and the third one lift and drag ratio, and all against the angle of attack. And Akram, I think what is very obvious here is that with increasing angle of attack, for sure the lift is increasing. Why it's increasing we will see just in some seconds. But at 30 degrees it seems that there is a drop, right?
Exactly. So it's like an airfoil or any aerodynamic shape. So when you start to increase the angle of attack, you will start to have more and more lift force because you are increasing the area, and because the lift force is proportional to the area. So when you increase the area, you will increase also the lift force. And at some point, when you reach high angle of attack, what will happen? You will have huge separation over from the body, and you will have a stall. So that's why you will have this really down force, and you can see clearly that you are losing a lot of lift force because of the separation, and it's clear from this graph. And if we jump to the second graph, which is the drag force, we can see that the drag force is increasing when we increase the lift force, and we can see from 20 degrees to 30 degrees that we have some increase in in the drag force, but we can see clearly from the 30 degrees to 35, where we have stall body, we can see completely that we have high increase in the drag force. And this is like based on the aerodynamic laws. When you will stall an object, you will have an increase in the drag force.
I think you can just test it yourself. If you're driving cars the next time, as a passenger, just hold on or put out your hand out of the window. And if you then vary like the angle between your hand, let's say, and the ground, you will see how the force acting on your hand is changing.
Yes, exactly. It's the most basic principle that you can test this idea with. So as Milad says, this will give you a clear idea about what's happened. So if you will increase the angle of your hand more than the angle where the flow is attached to your hand, you'll feel that your hand is like pushed down, and this because you have separation flow and recirculation behind your hand that will create pressure that will push your hand down. And it's the same principle here for the ski jumper and also for airfoil theory. So it's the same theory, and we can see this here clearly.
And if we take a look at the large graph, there we can see the ratio between lift and drag. And for sure, a high ratio is good because it means you have, let's say, high efficiency. But we can see here, and I think that is very important, if we take a look what are the forces doing. The drag force, in the end, is decreasing our flight speed. And the lift force is like holding the ski jumper up or pushing him up. And here you can see like that this lift-drag ratio is very much dropping. So Akram, I would say as long as you're below the 30 degrees, it's more like a control parameter you can use like to decide in which phase of the flight you are. If you increase the angle, you will lose more speed, yet you will also decrease your sink rate. But if you go above the 30 degrees, your lift will massively drop. And I think so the first lesson here, to put in a nutshell, is that there is a critical angle of attack, and once this critical angle is reached, it's not a good idea to increase it anymore.
Yeah, exactly. This is the point. And from this slide, we can see clearly in this last plot that we have the ratio between lift and drag force. And as Milad already mentioned, is what we call efficiency. This ratio is what we call efficiency. And if we have a value above 1, this means that we have more lift force than drag. But as you can see, after this 30 degrees, we can see clearly that we have values lower than 1, and this means that we have more drag than lift force, and automatically this object cannot fly far away if you have more drag than lift. So always when you design or when you decide on which angle you have to jump, it's the most important parameter to look at for. It's the efficiency, because it will give you a relation between lift force and drag.
Great, and now let's come to the good thing about CFD. You would maybe receive such results also from a wind tunnel test, but since we're doing a 3D flow simulation, we can also look into the flow field, what we're gonna do right now. So let me just go to the next slide. And what we can see here is a slice through the symmetrical plane of the ski jumper, and we can see the pressure distribution, where red stands for very high pressure and blue for a very low pressure. And basically you can see what is generating drag and lift. So we have this red to orange high pressure region, which is on the chest, or starting from the chest of the ski jumper, and we also have this blue low pressure region. And as you can imagine, this pressure difference between blue and red will result in a force, which is, like in this case, generating drag and lift. Let me just try to draw it. So since we have a pressure difference, maybe green is not the best color. So since we have a pressure difference, we will have a force here. And this force, you can split it up to lift and drag. And Akram, if we take a look at how this size of this pressure region is changing, we can really see the difference, especially between 20 and 30 degree, right?
Yeah, exactly. In this pictures, we can see like the middle slice of the pressure coefficient, or the static pressure here, and we can see clearly that we have this high pressure region in front of the ski jumper. It's significantly increase it dependent on the angle of attack, and we can see clearly that at 20 degrees it's not the same as 40 degrees, and we can see that this large bubble in front of the athlete, it's like a force that will push you back, and because of the low pressure behind the ski jumper, this blue region, we can see that this pressure difference, or this delta P, the pressure difference, this will create a force that directed to the free stream, and this athlete will be pushed back, and this is what we call drag force. And if you can see clearly from the two slices, from the 20 degrees, we can see that the blue bubble behind the ski jumper is like reasonable. It's almost the same as the high pressure in front, but if we can see the 40 degrees, we can see clearly that there is a high pressure in front of the ski jumper, and this in the meantime we have really low pressure from behind the ski jumper or the athlete, and this will increase the drag dramatically, and also for the 30 degrees. So we can see as much as we increase the angle of attack, we are increasing the separation, and we are creating a large bubble behind our athlete, and this will create high drag that will create problems for the ski jumper to reach far distance.
Absolutely. And if we go a slice further, we can also see the velocity distribution, which is not very interesting, I think, or not very special. The only thing you can see is like how this dead water zone is increasing, right? So at 20 angle of attack of 20 degrees, you have this very small separation bubbles wake structure, and with increased angle of attack, this becomes larger and larger. And this is especially, you can see it if you take a look at the ski, this lower blue area, which means very low velocity, is also increasing very much. But I think we should take a look at the total pressure, which is much more interesting, Akram. Because the total pressure is representing the energy of the flow. And so red in this case means it's fresh air. which is including the full kinetic energy. And when this air is striking or hitting the body, it loses some of its energy. And here we can see exactly where it's losing energy and also why.
Yes, exactly. So because you know that the kinetic energy is equal to half rho v squared, and also the total pressure, it's P, which is static pressure plus the dynamic pressure, which is half rho v squared. So it's the total pressure actually represents the kinetic energy. And in this flow, like Milad said, the red region represents let's say I'm gonna call it the clean air, where there is no disturbance in the flow, like the flow is moving with the free stream velocity, so there is no disturbance in the flow. And in this region where the red color is covering, it's the high kinetic energy. And if we can look for the other region where we have this blue to red to yellow color, so in these regions the kinetic energy is dropped. So we have loss of kinetic energy, and this is because of the shape of the ski jumper. So we have this wick behind the ski jumper, and if we want to reduce the drag, we have to take in consideration always to reduce this loss of the kinetic energy, to make sure that we will not we'll have always like smooth flow as much as possible. And this of course will have an impact on the drag and the lift forces on the athlete.
Yes, and if you can remember what I talked to you about flow separation, I think that's a very good example, because if you take a look at the back of the neck of the ski jumper, at 20 degrees you just have a very small blue area. I hope you can see it around here. And this one is increasing with the angle of attack. And this blue region it's an indicator, a very high indicator of flow separation. So exactly. You can just imagine let me try to take the pen if it works this time. So the flow is coming from here. And here it can't follow. And then we have a recirculation area here, which is creating a lot of drag, by the way. Really, a massive lot of drag.
Exactly, and the reason behind this is if we go back, I mean, just if you remember this concept that Mila talked about, the adverse pressure gradient, this is exactly what's happening here. So when you increase your curvature so high, then you will have this pressure difference, and then the flow cannot stay attached to the surface, and that's why you have this high or low kinetic energy bubble or separation region. So it's all about the right position of, or the right angle of the athlete according to the free stream.
Yes, definitely. And finally here, Akram, we can see the surface pressure coefficient distribution. Surface pressure coefficient means that basically it's the results are looking like pressure. It's still the pressure distribution on the surface, but we just make the values dimensionless. So 1 is the maximum value at the stagnation point. It's the point where the free stream is hitting the first time the body, and this makes it much easier to compare different flow states.
Exactly, and here it's really interesting view where you can see really nice thing that I want to mention here. So if we take the view of the angle of attack at 20 degrees, we can see that most of the air is hitting the helmet and the face and also the chest of the athlete, and this will create like a pressure drag, but mainly in this 3 regions, like the face and the chest, and a little bit in the legs. But let's jump to the other pictures for the 30 degrees and the 40 degrees, and especially for the 30 degrees, we can see clearly that the pressure is high almost all over the body of the athlete. So we can see that the chest, the belly, and also the legs are like there is high pressure over there, and this pressure will push the athlete back, and we can see clearly that this distribution will play large effect. And as we know, so if we just imagine like we will cut this shape of the ski jumper and we calculate the area over there, we can see clearly that the area of the last, or the angle of attack of 40 degrees will be much higher than the 20 degrees. And we know that the drag force and also the lift force is related to the area, the frontal area of the object, and from here we can conclude simply that the angle of attack will have huge effect on the forces acting on the athlete.
Yes, definitely. And there is another parametric study we did, which is maybe much more interesting. I mean, the angle of attack was somewhat trivial, right, Akram? But there is something else called the V angle. And as you can remember, the V angle is describing the angle between the skis. And as I told you, till the late 80s, everyone was using a angle of 0. And then people found out that varying the V angle has a positive effect. And I think this also comes clear when you take a look at these plots, right?
Exactly, and I was really surprised when I just checked the plot the first time, especially for the left force, which is like the most remarkable force here, because if we can see at 0 degree what we mean by 0 degree, it's like the feet of the athlete are totally parallel, so there is no angle. So the two ski plates are really straightforward to the free stream, and we can see clearly that we are generating like around 200 Newton of left force. But if we can see for the 30 degrees, we have almost like 35 Newton of force additional to the parallel position, or the 0 angle, and we can see clearly that this position increase the left force, and if you increase the left force, this will for sure give you more range to fly far away. And the interesting thing on top of that, because when we judge the performance of an object, we can't judge only with left force, but also we have to relate it to the drag. We can see that, of course, if you will increase left force, you will increase drag, but the idea is how much you will increase the drag. And we can see clearly that it's really interesting values, that the drag is increased, of course, when you increase the V angle, but the idea it's not really significant increase. So the efficiency and also the interesting thing we can see in the efficiency plot that at in the parallel degree we can see the efficiency is equal to 1, but at 30 degrees we can see that we have increased the efficiency, and this is like really interesting topic and really interesting point that we have to stop on and to talk a bit about it a little bit, because usually when you increase lift force, you will increase the drag, and if we will increase the drag, this means we will reduce the efficiency. But here we can see that the lift force is significantly increased than the drag force. I mean, the lift force is significantly increased than drag force, and this will result in high efficiency, and this is really important. And me personally, I was a bit surprised when I've seen the results for the first time. And of course, like the previous example, for the high angle, the 35 angles, we can see that we have the lift force is dropped, and we have lost completely the lift force, and of course the drag also is increased, and in consequence the lift, I mean the efficiency is decreased significantly, and we can see that we are going down from 0.5 to maybe less to 0.8, which is like really important for ski jumpers to reach far distance and to get far range. So this is the important thing that we have to stop on here. It's that this angle will increase the lift and also increase the drag, but the efficiency is really significant.
Yes, and I think that's a big difference compared to the angle of attack study. That if we take a look at the angle of attack, there is like a critical angle of attack, and which we should not reach. But Within this non-critical angle, the efficiency is nearly staying constant. And in contrast to that, the V angle seems to really have the optimum point, which is around
right.
30 degrees in our case. So this is a much better parameter to optimize, let's say, your flight posture. And here again, we have prepared several slices through the flow field. So first of all, again, the pressure. And yeah, I mean, I think first of all, what came into my mind when I took a look at this picture is that as long as you have a V angle of 0, your skiers are not like inside this plane. So, and I think that is in the end the very important thing about this V angle. By changing the angle of the skiers, you are also interacting or influencing the flow around the body itself, which you can see, for example, at 30 and 35 degrees. There we have this, you can see this high pressure and low pressure region generated by the ski. And this is interacting with the full flow of the around the ski jumper. And since, I mean, the angle of attack is not changing, everything else is still the same, but still the flow field is changing completely.
Yes, exactly. And here is really also a really interesting point that I want to talk about. So for the 0 degree, where we have the feet are really parallel to each other, the idea is, even if we will see here, we can't see the feet and the ski plates and so on, but we can see that there is this line of pressure in front. I think it's clear if you just, maybe Milad, you can show it to the audience. Yeah, exactly. This line, it's the line of the pressure that is created as stagnation pressure in front of the skis. And the idea what's happened here is because we have this pressure in front of our athlete, so the flow will not really go to directly to the athlete, and that's why we can see that the red bubble in front of the athlete is significantly low compared to the other positions, because we don't have enough air that goes directly to the athlete, and this because of the stagnation pressure that happened just in front of the skis. And actually this pressure have an effect on the lift force, and that's why we have seen that the lift force is significantly increased when we open the angle a bit, because this pressure is acting, if we can see that this pressure is not really parallel or in the same direction of the free stream, but it's a little bit from the downside, and this pressure region have two components of force, like the left one and the drag one, and if we can increase this red bubble in front of the athlete, this will of course increase the lift force, and that's why we have seen previously in this graph that we have increased the lift and a little bit the drag of the athlete when we opened this angle a bit, and it's because of the position of the feet and the pressure that's created underneath the skis.
Yes, and we can also take a look at the pressure field around the ski jumper. So what we're gonna now, we are changing our perspective. We're looking in front of the ski driver, and here below you can see this red line which is showing where our cutting plane actually is. So right now we are just in front of the ski jumper, and now we just have reached the start of the skiers. And left you can see, the left side you can see the slices for parallel, and the right for 35 degree. And
exactly, Milad, maybe I can just explain what's happening here, because when I start talking about this idea of the parallel position, maybe it was not clear, but here we can see this here clearly. So here, like, you can see that in the down picture we have this red line where we have this slice. And what's happened here, because when we have this parallel skis, so the idea what's happening is we have high pressure under the skis, and this will create like barrier between the two skis, and the air will not be able to flow in between the two skis because of this high pressure. And that's why the pressure in front of the athlete is low compared to the others. But if we can see to the other, if you can look to the other, the right side picture, we can see that when we open the angle between the skis, we create like a large distance between the two skis, and the pressure, the stagnation pressure under the skis is will not affect the air in between the skis, and we can see that there is more air that going just in between the skis. And even here in this picture, and we can see clearly that we have this spot in between the two skis. It's much higher in the right side, which is the high angle than the closed or the parallel skis. So here we can see clearly why we have this difference of pressure between the parallel position and with different angle.
Yes, and it's not only the distance, but I think a very important aspect is also the fact that it has an angle. So if you take a look, for example, when we have this V angle, the high pressure region below is moved to the center line, while the low pressure region on top is moved away from the center line. And this is related really to the V shape, because we have a change of the geometry, which we'll see in the next slides, I think, better. So
yeah, exactly.
Akram, maybe let's just go through them first of all, and then step by step. So here you just hit it the head of the ski jumper, and you can really see these larger differences. And if we go back here, you really see that basically it's not only the flow field of the ski jumper would change, but also the flow field around the skis. So we have a much higher low pressure region on top of the skis, which is creating additional lift.
Yes, exactly. I think that's right. Yeah, that's right. Absolutely, that this difference of pressure on the skis will create more lift. And actually, I'm gonna explain why. We can see clearly that for the parallel position, we don't have like high difference of pressure, but for the V angle, with V angle, we have significant difference of pressure, because for the parallel one, we can see that we have this stagnation pressure in front of the athlete, and this high pressure will affect the low pressure on top of the skis, and that's why this should be like low pressure, but because of the high pressure in front of the athlete, we can see that this low pressure is reduced. But from the other side, like Milad is showing now, we can see that because of this there is no effect, or there is no interaction, or there is low interaction between the high pressure in front of the athlete and the skis. That's why we can see that there is this wick, because this is like low energy flow there, and because of the difference of pressure between the lower part or the lower side and the upper side of the skis, this of course will increase the lift force and probably a little bit of drag for the athlete, and this is what we have already mentioned in the previous plot of the forces.
Okay, then let's move on. So here again, I think it's pretty much the same effect, Akram, right? That since the skis are in the near of the body of the ski jumper for parallels, that you have much more interaction and pressure exchange between the skis and the body, and therefore the
Absolutely.
low pressure region here is again smaller, and also the high pressure region. You can just, I think you can imagine it like, since the distance is smaller here, you have more exchange, right, between the areas.
Yeah, that's right. That's right. That's right. I totally agree.
And also, what is really interesting, that I would say there is the upper flow, let's say at the back, is nearly not changing, right? So we only have changes below the knees.
Yeah, and of course, this is exactly why we have this significant improvement in left force, because we can see that this, let's call it the blue bubble, or the low velocity region, we have almost the same. Maybe there is some small details, but we can see that we have an increase in the pressure from the from underneath the athlete, and it's really significant here. And this difference of pressure will create more force that will push our athlete to the up. So we'll push it up, and this will increase the lift force, and will give him like more range to like to fly far away and to get more performance.
Yeah, and if we take a look at a little bit what's happening behind the ski jumper, basically you can just see that we have different wake structures. But I would say basically that's the most important thing about the pressure Akram. I think what is more interesting is maybe not the velocity, but the total pressure, right?
Exactly. When we talk about, I mean, when we talk close to the body, like we were talking right now about like the pressure on the legs and the skis and so on, it's more important to talk about the pressure. But when we start to talk about the wick and what's going on around our object, it's more important to talk about the kinetic energy or the total pressure.
Yes, and first of all, what you can see, there is nearly no change at the head or at the head and back of the ski jumper. There's might a very small change, but the basic structure is looking the same. We have a small separation at the head, a small separation behind the neck, but I would say the main structure is looking quite similar, right? The only difference is this additional loss, which is generated by the ski itself.
Yeah, that's right, because I mean, for the 20 degrees, or I guess it's for the 0 degrees, maybe for the first one, I guess it's 0 degrees, because the legs are parallel. So when we plot our, or when we represent our slice in between the legs, so there is no touching between the skis and our slice. That's why we can see that there is no loss over there. But for the other degrees, like the 30 and the 35 or the 40, we can see clearly that we have some additional loss, because this the how it's called the skis are touching in this slice, and that's why we can see that we have another loss. But if we dig a little bit deeper in this picture, we can see that also this angle, or the V angle, it's far away from the helmet and the back of the athlete, but we can see clearly that there is some minor like effects on, especially in the 30 and the 40 degrees, that this blue bubble is a bit large than the 20, or I guess it's the 0 degrees.
Let's therefore take a look at the total pressure. So again, here we see slices for left side 0, right side 35 degrees. And we see the total pressure. So red means high energy or clean air, and green or even blue means a high loss of energy. And first of all, I think what makes sense, Akram, we have two vortexes generated by the skis, which we can see here, right? And I think what is very interesting, exactly, that if we have the parallel skiers, let me try to, yes, it's looking, if we take a look here, we have two vertices, which are, I would say, like this, right? But here, we got a very large one, and a little bit with distance a small one. So the whole structure of the vertex is changing.
Exactly, I totally agree. So for the first one, we have like, because it's like we have symmetric phenomena, like the vortices are created because it's parallel. So because what happened for these vortices are created because of the high pressure from the bottom of the skis and the low pressure from the top. So the airflow will try to escape from the sides, and when we reach these edges of the skis, the flow start to rotate like in any phenomena in fluid mechanics is called the vortex. And from the other side, because actually the flow is not, the free stream is not hitting like really the skis in the middle, but I'm going to call it dissymmetric phenomena, and we have like high vortex from the side and low one from the other side, and this because of the V angle between the skis.
Yeah, and if we go through, we can see like how these structures are affecting the whole flow field. And especially what I like very much is we can see here that this vortex is really opening.
And if you go a little bit back to the back, so probably in the end of the skis, there is an interesting thing, another step.
This one.
Yeah, here what we can see. Yeah, here what we can see. We can see because of the
converging configuration of the trailing edge, right?
Yeah, exactly. Because of this conversion shape, we can see that the vortices or the wick behind the athletes is completely different, and we can see clearly if maybe Milad, you can like draw it or maybe show it with the mouse, that we can see that the wick of there is this V shape of the wick of the skis from the side. We have these two.
Here, right?
Exactly. This is what I'm talking about. But from the other picture, we don't have this effect because the skis are parallel, so we don't have this V. And here exactly we can see this V shape.
Yeah, it's here.
Exactly.
Okay, great. Right, then, yes, I think also what you can see in general is this interaction between the flows. So how the wake of the body like is changed or manipulated by the flow of the skis. And here we can also see this V you talked about, Akram, I think more clear.
That's right, because here we are a bit forward in the flow, and like the flow is losing like the energy just over there, because when we go a little bit back, the flow will start to get his initial condition, and that's why we can't see this like significantly. But here, that's right, we can see this better here in this region.
Yeah, and just one last thing. I mean, we talked about small differences, right, of the flow behind this, and you can see it here. I think, for example, here you have some more blue regions. So there is effect, but a very small effect we can maybe neglect.
And exactly this point that you are showing now. So why we have this blue region behind the arms? I'm going to explain it like quickly here, because as you can see from the previous. I mean, in the parallel position, we can see that almost the position of the skis is the same as the arms. So what's happening is like the skis are covering the arms, so that's why we don't see this blue region behind the arms. But for the other one, because the flow is going from the sides, actually there is a flow that is hitting the arms, and that's why we have this recirculation region behind the arms. So the idea why we have this recirculation region or low kinetic energy region behind the arms of the athlete is because of the first one, or in the parallel position, the skis are like covering, let's say covering the arms, but for the other one not.
Yes, then, okay, I think this also you can just see the wake structures behind, and also that we have here like V-shaped. What's very quite funny, right? Here the wake structure is parallel, and here it's the V.
That's right, and we can see also that for the V position, we can see clearly that even at some point behind the athlete, we can see that the flow disturbance is still strong compared to the other one, and we can see that for the parallel position, or for the parallel configuration, actually the flow start to get back to the initial condition faster than the V position, because in the V position we still look that there is strong disturbance in the flow.
Yeah, exactly. And finally, we again have the surface pressure distribution for different V angles. And I think, first of all, what we see, Akram, is that what you talked about during the angle of attack study, that the air is again hitting, first of all, the head and the chest, right? And there is no change where the air is hitting the body.
Exactly. I believe that there is some really small details if we really look
the hand, for example.
Yeah, exactly, because I believe that the position of the skis will cover a little bit the body of the athlete and will reduce the stagnation pressure on the athlete. But I mean, it's not really significant effect, but there is an effect of that the skis are covering the athlete, especially if you look close to the legs and the bill of the athletes. It's remarkable. But rather than this, because we have almost the same position, I mean the same angle, the angle will not really affect the pressure distribution, like will not affect it like significantly, but there is minor affections.
Yeah. Okay, then yes, Akram, thank you very much. I think you will stay with us right for the Q&A. And now let's talk about your homework. As I mentioned, we will again provide you with homework assignments. And your homework assignment is, in this case, to prepare your own angle of attack study and investigate on your own the effect of a changing pitch angle. And therefore, we have prepared some material for you, which you will find on simscale.com, on our forum.simscale.com, and there is a category called Sports Workshop and here we have a tutorial where you will find like a description again of the physics, and you will find step by step how to set up the simulation on your own. And your job is to investigate at least 2 different angles of attack. You have 1 week time to submit this homework, and in the case you're struggling with a homework assignment or you need help, just reach out to us using the forum and we'll try everything we can to help you. I'm quite sure that there are some questions, therefore let's take the time to talk about your questions. First, just give me 1 second to check which questions we have so far.
I think we have a really interesting question here. It's about the closest surface, which is like, I think for athlete performance, it's a really interesting topic, and that's why we can see for the previous pictures that these athletes of the ski jump, they wear this really tight clothes and to avoid this flapping of the clothes, and this is really important. Maybe we can talk about it a little bit.
Yes, for sure. Just give me 1 second, Akram, and then first, yes, then let's start, Akram. There is a question by Sebastian Block. You mentioned, yes, what do you think? I know that they are investing a lot of effort for improving this clothes, right? So there's some special.
Yeah, exactly. I believe that for not only ski jump, but for all the sport applications, for cycling, for swimmers, also for ski jumpers, like the clothes are a really important parameter to play on. I'm gonna even explain it a bit more, because what's happening when the flow moving around the athlete, actually there is 2 forces that create this drag and lift force. It's the viscous forces and the pressure forces. In this investigation, maybe we have talked mainly about the pressure forces, but also we have the viscous forces, and the viscous forces are mainly like related to the interaction between the fluid and the surface of the body. And if we have this shapes and this flapping movement on the surface of the clothes of the athlete, this will automatically play a really important factor on the separation point and so on. And also there is another important parameter, which is the roughness of the suit, or what is called the clothes of the athlete. So also the roughness, and sometimes they use like special roughness patches to explain it a bit, to like create transition from the laminar boundary layer to the turbulent boundary layer, to make sure that the flow stay attached to the surface of the body. And of course, I'm going to say that this parameter is really important. Actually, for CFD, it's a bit difficult to investigate it because it's transient effect. Because if you look to the flapping movement of the clothes, it's really transient effect, and to do it, it's like can be quite difficult. So that's why usually they use wind tunnel to investigate this effect.
Yes, and another challenge is, if you want to create a simulation of such effects, you need to couple fluid simulation with the structural simulation, since you can imagine airflow is changing or is deforming the suit, and the change of shape of the suit is changing the flow around it. And this is something which is very complex, and I think especially for this case it will become really hard. Just because some people asked, we will send you till tomorrow an email including all information to the homework. So you will find a link to the homework assignment, to the tutorial, and all the other information you need. And there is a question by Vet. Vet wants to know, how about having a negative V angle? It will decrease the high pressure region on the chest area, but I was just curious. That's a very good question. I think, as you already mentioned, it's a trade-off in the end. And for example, a negative V angle would mean that you would decrease for sure the pressure on chest and the head. I think there are two reasons. I can imagine two reasons. First of all, I think it's not an aerodynamic reason. It will become very hard to land with such a configuration. But I think the main reason is that this would cause some other problems with aerodynamics, right, Akram? Because, I mean, you would hide the head somehow, but if you think about the configuration, this V is generating a lot of downforce because it's like a plate. If you would change it, you would get a pitch moment which in the other direction, which would make flying more difficult.
Yeah, exactly. And what's happened also, if you will create like negative V angle, what's happened is you will decrease the frontal area, and if you will reduce the frontal area, in consequence you will lose the left force, and also you will, of course you will reduce the drag, but we don't want to reduce the drag and we reduce the left force in the same time. And like I said before, if we will close the feet of the athlete or create a negative angle, what we will do, we will reduce the frontal area, and this will reduce the left force as well.
Yes. Okay, then let me just check. Yu Long wants to know, is the example of the ski jump a unique situation in sports, because most situations we are only interested in reducing the drag and lift is not an issue, accepting that in motorsports or cycling there may be a desire to increase downward pressure to increase traction? That's a good question, and honestly I don't know the physics about all disciplines in sport, but I think that motorsport is really unique, and ski jumping, right? I don't think that for example, in swimming you also use CFD simulations, or there you have hydrodynamics, and this is for sure only about drag reduction. So this
exactly. I mean, for taking care of lift force is just for some specific sports like the suit jump, this suit that they wear and they jump from an airplane. Here the lift force is really important. Also for ski jump it's really important. But for example, for example the next session will be about bicycle aerodynamics, and for bicycle aerodynamics we don't care about lift at all, and also the lift force is not important at all because there is no effect on the performance of the rider when we talk about or the cyclist when we talk about the force, and it's mainly about drag. So actually, yeah, the answer is yeah. Talking about lift force, it's only particular for such applications like the ski jumper, like the suit jump, and other applications, but not for all sport applications.
Yes, and there is a question by Mayuri, and he wants to know if change the helmet design would reduce air separation, hence reduce drag force. Yes, I think that's definitely an option, and I know that the manufacturers of these helmets are investing a lot of resources in optimizing the shape to reduce the drag. But since we want to do a parameter study, we did not touch the helmet and use the same design. But for sure, I imagine that there is a high potential for optimization. And if you take, for example, a look at the helmets which are worn by cycling drivers, you can see is how much time they spend for develop every detail. Well, it seems like we don't have any more questions, and we are 20 minutes over the time, so thank you very much for joining. Hope to see you next week when we are going to talk about aerodynamics of a bicycle. Yes, hope to see you next week. We will send you information about the homework soon. Have a nice day. See you soon. Bye.